Okay, so let us start the my second lecture. So yesterday we discussed that for non-equilibrium problems we can look at this generating functional for fields defined on this double contour, and so this is defined as follows, which you can so drawing diagrammatically is like this. So essentially you have some initial state rho 0, and then you run, say, let's do from time to minus infinity to plus infinity, and then you trace all possible configuration here, and then you come back, okay, and you come back, and then so this is the so even though I separate these two contours, they should be thought of as on top of each other, okay, and so separate them just to highlight that these are actually two contours, and so you can write it in the say in the Schrodinger picture. Then this is like you have a unitary you have a evolution operator from minus infinity to plus infinity, and then I can take on some source on the first leg phi 1, and another source for some operator, say on the second leg, which we call phi 2, and then my evolution operator then will be deformed by this phi 1 for the first leg, and then for the second leg will be deformed by phi 2. Okay, so that is this object, and I can also write it in terms of so-called the which I did yesterday. Write in terms of the say interaction picture, which is just path ordered exponential I say phi 1 or 1 minus phi 2 or 2. Okay, and also you can introduce this so-called RA variable phi 1 plus phi 2 and phi 1 minus phi 2, similar for O. Okay, similarly for O, and and then you can then this just become trace rho 0, then path ordered, then exponential I O R phi A and plus phi R O A. Okay, and so when you now take derivative over phi A and phi R, then you get OA and OR. So as we discussed yesterday, that this actually gives you a complete set of the fluctuation and the response functions. Okay, so they capture really a very wide class of physical observables. And so if you write this more explicitly, suppose you have a theory, and if you write this more explicitly, then you can write it as, then say suppose you have some theory with dynamical field phi 1 and phi 2, then you need to double your degrees of freedom, because now you have two contours, and then you can write it as phi 1, phi 1, phi 2, phi 2. Okay, so phi 1, phi 2 are dynamical field, and this phi 1, phi 2 are the sources. And then S0 is the fundamental Lagrangian. Okay, so this just essentially defines this path integral fundamental action. So this is your UV action. So this is a macroscopic action. Okay, so macroscopic action. Okay, so so from here, you can from this definition, you can immediately deduce some properties of this W. So you can immediately deduce the property of the W. So let's imagine, let's take this operator to be Hermitian. And then suppose now you take a complex conjugate, okay? So now you take a complex conjugate. And then because this is a unitary operator, and the real is Hermitian, then you immediately deduce that the W star phi 1, phi 2 should be equal to W phi 2, phi 1. So essentially you exchange them, okay? Because when you take the complex conjugate, then this one goes to the before the 0, and this becomes that. Then you just exchange phi 1, phi 2. And similarly, you can also see that you so this is the first property, and you can also write it in terms of this RA variable. Then you get phi star, phi R, phi A, then relates to phi R, then minus phi A, okay? Because now when you exchange phi 1, phi 2, and then the antisymmetric variable will change sign. So antisymmetric variable will change sign. And so this is the first property, and there's and another property is that now suppose you set phi 1 equal to phi 2. So I set them to be the same, and then that two unitary operator become the same. Then when you take the trace, and then this should become 0. Okay? Then because the trace of the 0 equal to 1, so this becomes 0. So in other words, the W phi R and the phi A set to 0. So when you set to be the same, then say phi A is set to be 0 when phi R equal to some phi, and this should be equal to 0. Okay? And this tells you, okay, this tells you. So now remember, when you take derivative over phi, so remember when you get the correlation functions, then you take derivative over phi A, you get OR, a correlation function of OR. When you take derivative over phi R, you get OA, and then in the end you set the source to 0. Okay, so this immediately tells you that so when you take derivative over phi, when you set phi A equal to 0, it's identically 0. Okay, so that means all the A correlation functions which only contain A variable must be identically 0. Okay, just based on kinematics. Okay, and yeah, and this is just a consequence of the kinematics and the unitarity. Okay, good. So now this is our starting point. And so now we would like to imagine, okay? So now I would like to imagine that I take this source to be slowly varying, okay? I take this source to be slowly varying. So I'm only interested in the long distance and the long time physics, okay? Take slowly varying, and now I want to derive a low-energy effective theory. Imagine to derive some low-energy effective theory for this kind of system. So what now I will do is I will now separate my dynamic field. Okay. So I imagine I separate into two sets. One is the fast variables, and another set is slow variables. Okay. It's slow variables. And now let's imagine, of course, there are two copies of them. And now let's imagine we just integrate out the fast modes. Okay. So let's just imagine integrate out psi modes. Okay. So we integrate out the psi modes, then original path integral then just become, so exponential W phi R phi A just become, then you can write it just as a path integral of the slow modes. So in general, there are again two copies of them, and then you will have action just for the slow modes. Okay, So chi and phi. Okay. So then this will be your Lorentz effective action. Effective action, yeah. Okay, yeah, just effective, yeah, Lorentz action. Okay. Of course, in reality, you can not do this explicitly. So what we want to do is we want to find the physical criterion to so that we can determine this thing on physical grounds. Okay, on physical grounds. So now let me just make some remarks on the some general remarks on this effective action. So the first remark is that even though so when you integrate out the degree of freedom, those massive degrees of freedom, those fast degrees of freedom, after integrating out psi, and this effective action depends on the zero. Okay, depend on initial state. Because the information about the initial state now also will go into your effective action. Will go into Lorentz effective action. So remember, your UV action is actually independent of your whatever state you consider. But now, after you integrate it out, but in this path integral, your initial condition depend on this state. Okay, depend on states. And now, when you integrate out those fast degrees of freedom, then now your effective action, of course, will depend on information about that state. Okay. So in principle, I should make it explicit that this depends on those zero. But yeah, just for rotational simplicity, I will not put it there. So this is the first remark, and the second remark is that where in the fundamental action, so these two parts, the action are factorized, okay, because you essentially just have two path integral, and then these two patch are linked by two boundary conditions. So one is the boundary condition, the initial boundary condition, of course, is determined by your state, by the wave function of those zero, and then there's a final boundary condition, which is that we have to trace everything here. So trace everything here means at here, phi 1 should be equal to phi 2 at t equal to infinity, okay, to path infinity, okay. So in this path integral here, you have to impose this trace, okay. You have to introduce this trace in this path integral, and so these two copies are linked, but the action themselves are factorized. But now, when you integrate degree of freedom, then S effective chi 1, chi 2 will no longer be factorized. Okay, so there will be couplings actually between chi 1 and chi 2. Okay, they're no longer factorized. And so you can easily check it yourself. Just to do a harmonic oscillator example, take two harmonic oscillator. And then when you double it, then of course you get four. Take two harmonic oscillators, then you integrate out one of them, and then you actually will find actually this in general will not be factorized. Okay. Good. So again, the procedure. So as I said, that in general we cannot determine this precisely. So our goal is to find physical principle to determine it. Okay. So before telling you how to determine it, so let me just mention one other remark. Is that, as we said yesterday, say we start from a UV theory. So this is your S0. Okay. And then we want to find the macroscopic behavior. So this effective action then should be considered defined below some cutoff. Okay, so imagine you have some cutoff here. So the choice of lambda, of course, depends on your specific systems, and the lambda should be say low enough so that the dynamical variable, say this chi, can already capture your low energy physics. Okay, but the lambda of course should be far from UV as far as possible. Okay, so it's some intermediate energy scale, and then this effective is the Bass theory, what we normally call the Bass theory at the scale lambda. Okay, and now if you want to go to the macroscopic low energy physics, then you do RG here. Okay, you do RG here. Okay, so normally when you write down your low energy effective action, say you do some derivative expansion, and then in principle there are infinite number of terms here. Okay, but when you do this RG, as we know that only a finite number of relevant terms will be important. So in the end, even though in principle this contains infinite number of terms when you integrate out things, but for all physical problems, there will be just finite number of terms will be relevant at low energies. Okay. Okay, so now let me just remind you the criterion, the general principle we use to write down S effective. So this again is the three. So this is the same as the in the free energy case as in the equilibrium case. First is you identify the slow variable chi. Okay, and then the second is you identify symmetries. You must impose symmetries or consistency conditions. Okay, and the consistency conditions. Okay, and then the third thing. So for here you can already from these two you can already just write down the general action. But sometimes we also have to be careful about the integration measure. Okay. Because when I write this, normally when you do this kind of path integration, that will also affect this integration measure. So you have to be a little bit careful about that. Okay. So as we discussed yesterday, that to identify chi, so this step comes from your physical input. Okay, from your physical input. As we discussed yesterday, that the conserved quantity always leads to slow modes, and so that would be the starting point, say, to look for such kind of chi for the conserved quantities. So now let me just mention a few words about the symmetries. Okay, so now let me mention a few words about the symmetries and consistency conditions. Okay. So of course, if your system, whatever symmetries your system have, then you should of course impose in this low energy effective action. Okay, should impose this low energy effective action. And so as a general principle, let me just separate the possible symmetries, say in terms of global symmetries. Say some continuous global symmetries. Okay, so if you have global symmetries, even if you have two copies, okay, you have two copies, but because of this boundary condition, because you have to identify the field at infinity, so that means what? But the global symmetries are independent of space-time. So that means that the global symmetry should act on the first leg and the second leg in the same way. Okay. So if you have global symmetries, should act on two copies the same. Okay, due to the boundary condition, the chi1 at infinity should be the same as chi2 at infinity. Okay, but if this chi also has local symmetries, which we will actually see examples in the hydrodynamics case. Actually, there can also be local symmetries. In local symmetries, because local symmetries depend on the space-time, so then you can actually say, if you consider the small, so-called the small gauge transformations, and then you can actually make the gauge transformation to vanish at t equal to infinity. Okay, and then that means for local symmetries, then you can do the so there's only one copy of them. But for the local symmetries, and then can act on chi1 and chi2 independently. Okay, for local symmetry, you actually can act on chi1 and chi2 independently. So actually, we have two copies of local symmetries. Okay, and there are two copies of local symmetries. And so you should say, if you have local symmetry, then you should act on two copies of them. And now you can also impose discrete symmetries. So there can also exist discrete symmetries. So of course, for the standard, say, charge conjugation or parity, and these are all global symmetries. Of course, you only you should only impose one copy of them, and to be the same on the both legs. Okay, so this aspect is the same, and so those can be imposed straightforwardly. But suppose your system also have something involving time reversal. Okay, suppose also have something involving time reversal. Then of course you should also suppose S0. Say if your original action and the rho 0, say, have time reversal symmetries, and then of course you should also impose that time symmetry in your Lorentz effective action. Okay, but actually impose the time reversal is now, so time reversal T, let me use let me use script T, and so to separate with temperature. So this is actually more subtle to impose. So later I will make this precise, but intuitively this is more subtle to impose is the following. Is that if you have a general density matrix, okay, so then you integrate out some fast degree of freedom, then they are almost always in your Lorentz effective action. Then almost always in the Lorentz effective action will be dissipative. So there will be dissipative term here. So you know, whenever you have dissipative terms, then time reversal is just broken. Okay, even if your original series is time reversal invariant, but in this macroscopic Lorentz action, the time reversal has to be broken. Okay, so now, so that means imposed time reversal is actually tricky. Okay, but the imposed time reversal is important. It's important because we know that, for example, even in the linear response, Ansag pointed out in the 40s that the response matrices, linear response matrices, must be symmetric if we have time reversal symmetry. And so this is so-called Ansag relations. So the time reversal is important, but cannot be straightforwardly imposed. Okay, so we will explain a little bit later how we do this. Okay, how we do this. But the rest are straightforward to do. Okay, the rest are straightforward to do. Okay, so all those symmetries, other than those, are not different from your equilibrium systems or from your standard effective field series. But there are some new elements here, very specific to because we are defining a theory on that kind of contour. Okay, so now there are new consistency conditions. Specific to effective field theory on the closed time path. Yeah, on the closed time path. Okay, so CTP means the closed time path on that kind of path. Okay. So now let me now explain those new consistency conditions. So let me first write them down and then I will explain them. Okay. So you can show that for any theory, for any quantum mechanics, for any quantum system defined on this kind of quantum, and when you integrate out some degree of freedom, the remaining effective action, okay, the remaining effective action should always satisfy the following condition. So should always satisfy following condition. First one is so chi is the slow mode. Now I will use the RA, this R and A variables. Remember, phi is the source and chi is the slow mode. So when you take the complex conjugates, then you find that this is equal to minus S effective. And then you take the R field does not change, but you switch the sign of the A field. Okay, of the A field. So this is the first condition one has to satisfy. The second condition one has to satisfy is the imaginary part of this S effective. So first, this condition tells you that S effective must be must contain a complex part. Okay, must contain a complex part. And then the second condition is that the imaginary part must be greater or equal to 0. Okay. And the third is that S effective. And now if you set all the A variables to 0, then this must be identical to 0. Okay. So it must be identical to 0. So the condition 1 and 3 on the counterpart of these two conditions for the full generating functional. Okay, so this is for the full generating functional, and but at the effective action level, they should also satisfy that condition. Okay, so you can prove this at the formal level for any systems for any density matrix. Okay, but the proof is actually not very long. Just take a few minutes. But to save time, I will consider a slightly simple case, which only take 1 minute to prove those properties. And that can already give you some conceptual understanding where those properties come from. Okay? It's already enough to give you some conceptual picture. So let me just consider a simpler situation. Consider a simple situation, which this initial density matrix, rho 0, this initial density rho 0 is factorized between the fast and the slow degree of freedom. Okay? So it's factorized between fast and slow degree of freedom. So suppose the rho 0 is factorized between chi and psi. Okay, so that means I can write my rho 0 as a density matrix for psi and the density matrix for chi. Okay, density matrix for chi. So now my full generating functional is given by u dagger phi 1 or u phi 1 rho 0 psi, rho 0 chi, and u dagger phi 2. Okay. So this is my original generating functional. And now what I want to do now is I want to integrate out the psi. Okay. But now since this is since now they are factorized, this is trivial to do. Then I can just written as the following. I can just written this as trace the 0, it traces over the the Hilbert space generated by the chi degree of freedom, and the 0 chi, and then the rest by the rest object obtained by integrate out the psi. Okay, which let me call it A. So written more explicitly, A would be the trace over the psi Hilbert space, like U. So let me now the U. Yeah, let me call this U fast. Okay. So this is the evolution operator only for the psi degree of freedom. Okay. So now let's look at this evolution operator. And now suppose if we only integrate out the psi, and now you can essentially treat all the dependence on chi as if chi is just some kind of external field. Okay, it's just some kind of external field. So after thinking this chi as some external field, and then this will be just some kind of evolution operator for the psi degree of freedom. Okay, so let me just write it as U fast, and now we are dependent on phi 1 and the chi 1. Okay, and then 0 psi and the fast dagger, which phi 2 chi 2. Okay, so chi 2 now also just like an external field. Okay, not just like external field. And this, by definition, I will define as my S effective. Okay, so this is just trace all the degrees of freedom psi defined as my Lorentz effective action. Okay, yes? Is this a modeling issue? Not really, because because you can all write all of them in terms of the you can write it in the path integral form. Write it in the path integral form, then they all commute, and then essentially just like something like this. Yeah. Any other questions? Good. So now the trace over the psi degree of freedom then can be simply written as such an operation. Okay. Written as such an operation. And now immediately, if you take a compressed conjugate here, and then you just get this one, okay? And again, because that these are the unitary operators, okay? These are unitary operators. And when you take the compressed conjugate, and then again just change, just like you exchange phi 1 chi 1 with phi 2 chi 2, and then the symmetric part does not change, and the antisymmetric part switch sign, and the minus sign is due to the I in the exponential, okay? And now the second condition just come from this is a unitary matrix. This is a unitary matrix, and now this is a unitary matrix which you involve in one side is one unitary matrix, but it's another unitary matrix in the other side. Okay. And now because rho 0 is normalized, and this is just like something called fidelity, okay? And if rho 0 is a pure state, then this is what people call fidelity, and it means you evolve with some unitary matrix, and then you evolve back with another Hamiltonian, okay? And then just from the Cauchy-Schwarz identity, from Cauchy-Schwarz inequality, you can easily show that this A must be smaller than 1, okay? So that means that the imaginary part of S effective should be greater or equal to 0, okay? Again, 0. And the third one is also easy to see. When you set phi 1 equal to phi 2, chi 1 equal to chi 2, and again this becomes the same operator. When you take the trace, then this becomes 1, okay? Then this become 1, become identity, and then that S should be equal to should be 0. Okay, so you also prove the 3. Okay, just set phi 1 equal to phi 2, chi 1 equal to chi 2, then 2, 3. Okay, so in the end, these 3 properties all boils down to the unitarity. Okay, boils down to unitarity. So you can consider this as the consequence. Okay, so this is the Yeah. So this is the consequence. So 1, 2, 3 are the consequence of quantum unitarity, unitary time evolution. Okay. So this is not something you normally see, say, for doing a equilibrium partition function. So there, you don't really have a unitary evolution, and yeah. So this is an intrinsically a Lorentzian concept related to the real time. Okay, related to real time. Any questions on this? Oh, it's just real time. Yeah, real time evolution. This is just related. These are the unitary operators. Yeah, when you do the unitary evolution, somehow that put a constraint on your low energy dynamics. And the one thing let me just mention, all three conditions is just related to the general structure of the action. They actually survive also when you take the h bar goes to 0 limit. Okay, and suppose you want to consider the classical limit, which then we just consider a classical statistical system. And then actually those conditions also survive the classical limit. And then somehow this quantum unitarity actually also impose constraints on the classical statistical system. If that system have a quantum can come from a limit of a quantum system. So now let me just mention the implication of this, quickly mention the implications of these three conditions. So for simplicity, let me just write this. So now let me just write this as capital phi r and phi a. So this phi r now is the collective of the source and the dynamic variable. Just just I collect them together to save notation. Okay, save notation. So let's first select one. So as I said, this actually implies S effective must be complex. Okay. In particular, if I separate this S effective into the odd and the even part in the A field, okay. So this is an odd number of A fields in number of phi A, and this is even in number of phi A, okay. Then S effective odd, then from there, so when this is odd, that means when you switch Ka phi A to minus sign, so this will change minus sign, and then we cancel with that minus sign. So that means that S effective odd must be real, okay? And S effective even must be pure imaginary. Okay, so this is a key, will play a very important role later. Okay. So you find that the odd terms are always real, but the even in this capital phi A terms, they should be always pure imaginary. And so now let's look at the original action. So original action is factorized. So original UV action is factorized. And now if you write this in terms of phi r, and if you write in terms of this r and a variables, then this is always odd. And so this is real. Okay? So this is real. So this is related to your original action S01 minus S02, which is anti-symmetric between the two. This is odd, and so this is real. But now when you integrate out degrees of freedom, integrate out the massive degrees without this fast degrees of freedom, then you will in general generate terms which are even in this A field. Okay, generate term in even A field, and then this tells you that those even terms must be pure imaginary. Must be pure imaginary. And furthermore, those even terms, their imaginary part is constrained to be greater than 0. Okay? To be constrained to be greater than 0. Yes?
Pure imaginary again, which one of these conditions implies that?
Oh, yeah. Sorry, maybe I'm too fast. So remember, this is just phi r. The whole thing just phi r. And this is phi a minus phi a. So if this thing is odd in phi a, and then there will be minus sign coming out, and then S star will be the positive and the S itself, and then that will be real. But if it's real even, and then this minus sign is still there, and then this should be pure imaginary. Yeah.
So what is the originate always odd?
Yeah. So the original action. So before you integrate out anything, so the S effective at the UV is just S01 minus S02, okay? And this is always odd when you exchange 1 and 2. And so that's related to your original action is real, okay? But now when you generate even terms, which are even in exchange 1 and 2, and then those terms must be pure imaginary.
But here you exchange both
Yeah, that's right. You have to exchange both sources and the dynamical field. Yeah. Good. Okay, good. And okay, so this is the first consequences. So the second consequence is that somehow those even terms must be greater than 0. Okay. So later we will see actually this is responsible. This is responsible. So later, okay, not now you will not see it. This is just a commercial. This is just commercial. So later you will see actually this is responsible for the second law. Actually, the entropy actually increases with time. Okay, and also you will see this is responsible for the causality. For the causality in the sense that if you generate turn on a source, and then you look at the response, and the relation between the source and the response are given by the retarded Green function, means that the pole they are all in the lower half plane rather than in the upper half plane. Okay. And that is also responsible, and this is also responsible for that. And the retarded nature of the response is also by that. Okay, so to say in some fancy language, this one is the one which gives you an error of time. So you have a thermodynamic error of time, and you have a causal error of time. Okay, so you have these two error of time, which this is responsible for that. And the consequence of this third condition, means that if you expand, means that no term in S effective depends on phi r only. Okay, just any term in the effective action must contain at least one factor of phi a. Okay, so must contain. All term must contain at least one factor. Okay. So these are the consistent conditions which are. So these conditions are universal, in the sense that they should be satisfied. They should be satisfied by the right. Okay. For some reason my notes was in in disorder, become a disordered system. Anyway, so these are universal. So these three consistencies are universal, should be satisfied by any quantum system and any density matrix. Okay. So now let me discuss. So far, apply to any rho 0. Okay. So now I will consider the time reversal. Okay. Now let me tell you how to do the time reversal. Okay. So now let us imagine. So now let us imagine the system at the microscopic level. Okay, at the microscopic level, say your S0, then has a time reversal symmetry. Okay, so does not have to be time reversal itself. Say suppose it's invariant under discrete symmetry which contain the time reversal. Okay, you can also have other factors. You can have C and P, CPT, etc. But just have to contain at least one T. Okay, at least contain the time reversal. Okay, yeah. Suppose at the microscopic level, this is a symmetry. Okay, suppose this is symmetry. And now let's look at the fact that your original. Now let's look at the consequence that this is a symmetry of your original theory on this generating functional. Okay, on this generating functional. So yeah, let me just erase this. So it turns out, so this you can do just using the standard. You can just use the standard trick. Okay, you can use the standard trick. Just insert the theta and theta dagger into this trace, and then just act through all these operators. Okay, then you can just work out the consequence of the time reversal symmetry. And now suppose it turns out, if theta 0, if rho 0 is theta invariant, okay, if rho 0 is also theta invariant, so if your density matrix is also invariant under this time reversal, okay, and then you find that this exponential W, which I see defined to be rho 0 phi 1 phi 2, now on the time reversal operation, okay, now it's mapped to a different generating functional, which I denote as W, which is defined by the following contour. Oh no. So I have to, yeah. Okay, so map to something like this. Map to something like this. Okay, so now the rho 0 is defined as t equal to plus infinity, and now the source now acts upon the so phi theta, phi 1 theta, phi 2 theta is just simply the action of the this theta operation on those sources. Okay, and the action on the source is defined according to how the theta acts on the bounding operators. Okay, so you find going as this. So this I define to be, say, exponential Wt. So it's a time reversed process. Okay, so phi 1 theta and phi 2 theta. So this tells you that the time reversal actually does not bring W to itself. Okay, so the time reversal does not put constraint on the W itself. it only relates W to a time reversed process. Oh, of course, this makes perfect sense. So that means the time reversal by itself only relates as effective for a time reversed process. Okay? Okay, cannot act on S effective itself. And so this is consistent with our expectation that this is dissipative. Okay, this is dissipative. The time reversal should not have a simple action. Okay. So naively, it seems like we are doomed because now you cannot act. So now it seems like you cannot act time reversal. Okay, but actually there's a way out. Now there's a way out. So before we find that way, I have to order my notes. Sorry, give me 1 minute. Okay, good. Okay, good. I think. Yeah. Okay, good. So now it turns out that the way out is to impose another condition. Okay, it's to impose another condition. So as we said, when we consider a long distance and long time physics, we expect the system to be in local equilibrium. Okay? We expect the physics to be local equilibrium in the following sense. So let's consider you have some, say some, let me just use this to denote you have some kind of configuration, okay? Non-wavelength configuration. So this is just your typical, a typical length scale of your physics, which changes, okay? And suppose let's look at the distance scale L, which is much smaller than the variation of your physics, but much larger than your UV cutoff scale. Okay, so this UV cutoff scale. So for example, in general, maybe take to be say temperature or say mean free. 1 over lambda can be mean free time, etc. Okay, suppose at such distance and time scale. Okay, at some scale. Yeah, I'm using a relativistic notation, and for non-relativistic system, they can be different by some factors. Yeah. Anyway, yeah. So then at such kind of time scale, at this kind of such kind of distance and time scale, then the system should be in approximate equilibrium. Okay, should be in approximate equilibrium. Okay. So now the question is how do we impose such kind of equilibrium? Okay, and how do we impose such kind of local equilibrium? And so the way to do this is the following. Even though we expect, yeah, let me just first make a statement. We expect local equilibrium systems. Yeah, let me say slightly differently. Yeah, suppose. Yeah, so the local equilibrium systems the corresponding rho 0 in principle can be many different kind of states. For example, can in principle even be a pure state. Okay, say for example it be a pure state. For example, a typical macro state due to a black hole can be considered as a local equilibrium, because when you look at the local behavior, it's always like thermal system. Okay, and so we expect actually there will be wider variety of these local equilibrium systems. But in order to get intuition how to impose this local equilibrium condition, we can look at prototype systems. Okay, so we can look at the prototype systems. A prototype systems is just a thermal density matrix perturbed driven by external source, driven by slowly varying external source. Okay. So if you have thermal equilibrium and now you drive it by some external sources, say for example turn on a very slowly varying electric field, and then the system will be driven out of equilibrium. But again, from this picture, if the wavelength of that electric field is very long, and then we expect the system should be in local equilibrium, okay, to be in local equilibrium. So this is a prototype of a local equilibrium systems, okay, a local equilibrium systems. But now if we can deduce this local equilibrium condition on such kind of systems, and that should be immediately generalizable to the general local equilibrium systems. Because the concept of the local equilibrium does not depend on the global structure of a state. So whether it's a pure state or density matrix should not matter, okay? And should not depend on that kind of global structure. So once we deduce how to do this prototype, and then we should be able to do it for the general system, okay? So now I will just derive the condition for the thermal density matrix driven by a source, and then we can just generalize to general systems, okay? So in this case, then I will just take rho 0 to be given by the minus beta H0. So H0 is your Hamiltonian before you turn on the source, okay? Before you turn on the source. So now the fact that rho 0 is given by this particular form, okay? So now their Liu consistency conditions should be satisfied by W. Okay, so now they're Liu consistency conditions. So they're not Liu consistency conditions. So this is normally called a KMS condition, okay? After the Kubo, this is a Kubo-Martin-Schwinger condition. So at 2-point function level, this is very familiar to people. So let me just remind you, quickly remind you. Let me do it here. Yeah. So at 2-point function level, suppose I have this 2-point function, beta H0, say AT and B0. Okay? So now I can now insert identity here. Okay, so I can just write it AT, exponential beta H, exponential minus beta H, so, and B0. Okay? And now this has just become AT shifted by I beta, by minus I beta. Okay? And then this now just become 1 over Z0 trace A T plus I beta. Yeah, just become trace exponential minus beta H0 B0 A T minus I beta. Okay? So now, because of this density matrix have this special form, so now I have related this correlation function to this correlation function, but now with the time shifted in the imaginary direction. Okay? A time shifted in imaginary direction. So notice that the order of these two operators have changed. Okay? The order of these two operators has changed. So now we can apply. So now we can apply these to the general situations. Okay. So now we can just apply this to this generating functional. Okay. So now we can just apply that to that generating functional. So the calculation is trivial to do. So essentially, you start with your original phi 1, phi 2. So you have a trace 1 over 0. Then you have exponential minus beta h0. So now we have anti-time ordered, the minus I phi 2, O2, and the time ordered I phi 1, O1, okay? So this is my, and again I will just insert here, exponential minus beta h0 and exponential beta h0. Okay, just do the same thing. And now what you find, okay, so according to our original rule, the t tilde is before the t, okay? So the t tilde is before the t, okay? Yeah, t tilde is before the t. Yeah. And now if you do this, just exactly the same as here, okay? So you will find this now become trace, now exponential minus beta 0. You change the order between them. So this is t, exponential I phi 1, O1. And then for t tilde, now shifted by imaginary time. O2 times phi 2 t minus I beta. Okay? So now the key thing is that now the order of them have shifted. So that means we are no longer the original W. So the original W, the anti-time ordering is before the time ordering. So now we actually go to this case, which time ordering is before the anti-time ordering. Okay? So now this is actually become WT. So now this become differential WT phi 1, phi 2 minus I beta. Okay? Again, when you do a ChemS, when you use that the system is in thermal ensemble, then you find actually you relate W to WT. Okay? WT. And by itself, again, you cannot impose this condition, because it relates something W to WT, not to W itself. But now we have two equations. So let me call this equation 1. This is equation 2. But now if I combine 1 and 2, then I can actually relate back to W itself. Okay? So I cannot impose either time reversal or ChemS separately. I have to combine them. That's the only way. And when I combine them, then W go to WT through a time reversal, and then by ChemS, then we're back to W again. Okay? So if I combine now W1 and these two procedure, so now combine 1 and 2. So now I find, then I derive that now I have a consistency condition, phi 1, phi 2 equal to W phi 1 theta T and phi 2 theta T minus I beta. Okay? And now this is the condition acting on W itself. And this is the condition acting on W itself. And now we can impose such a symmetry. Now effective action then should satisfy such a symmetry. Okay? Should satisfy symmetry. And this symmetry will impose simultaneously consequence of time reversal and the local equilibrium. Okay? And local equilibrium. So I want to keep that, so let me just do here. So now I have these 4 conditions. Now I also have to, now let's work out how this should imply on the dynamical fields. Okay? So now this is a condition which W must satisfy, and then now we have to since the W is since W is expressed in terms of the path integral of the chi, and then we will see how this should impose, how we should act on the chi field. Yeah, first I emphasize this is a Z2 operation, okay? This is a Z2. Okay, this is a Z2 operation. Yeah.
If you apply KMS twice, you get back.
Yeah. Yeah. So if you apply this operation twice, you get it back to itself. Yeah. Yeah. So if you apply it twice, you automatically get back to itself. You automatically get back to itself. So that's a Z2 operation. And then when you act it on once, then we impose this, and then this becomes a symmetry. Yeah. Any other questions? Good. So I think. So when should I stop? Is the? Oh, it's 5. 5. Okay. Good. That means I have. Then I may have time to talk about the example. Oh, maybe, yeah. So let me just, maybe I should not have erased here. Or maybe I just keep this box. Okay, keep this box. Okay, so now let's see. So now let's consider a simple case. Okay, so the S effective. So since it's W equal to d chi, S effective chi, then S effective should ensure this equation star. So let me call this equation star. Okay, so effective should be equation star. So this is easy to see if suppose in the S effective the dynamical field coupled to the source in a very simple way. Okay, so let us consider a simple situation that in the S effective the dynamical field action can be written just a pure dynamical action and then coupled to the source in a very simple way. Okay, so let's imagine the coupling is just a standard simple coupling between the source and dynamic field. Okay, so this works for the generic situation, say if you consider all the parameter, etc., near phase transition, but actually this does not apply to the hydrodynamic situation. In the hydrodynamic situation, the coupling between the dynamic, we will see that in the hydrodynamic situation, the coupling between the source and the dynamic field are much more complicated. But let's just consider this simple example first. Okay. So now we want the W to satisfy this property. Okay. So now you can just easily convince yourself. Okay. You can just easily convince yourself. Then the star can be satisfied if S dynamical part chi1, chi2 satisfy the following condition. Again, it's a Z2 symmetry equal to chi1 equal to chi1 tilde and chi2 tilde, and the chi1 tilde and the chi2 tilde is precisely just chi1 theta, and the chi2 tilde is just chi2 theta, say t minus I beta. Okay? T minus I beta. And if the dynamical field satisfies this condition, and then this W can be satisfied. Okay? So we want this. So we need to impose this additional Z2 symmetry to the action. Okay. Any questions? Yes.
So how do I see that star equation is C2?
Oh.
If I apply it again, it seems like I have 2i.
Yeah, so you apply again, you will find that this, no, you have to add this operation, and this operation reverse time direction. Yeah, let me write it more explicitly. for one case. Okay, just to this is a good question. Let me just but this is also important question. So let me just write it explicit for you. Let me just anyway, I cannot find it. Let me just write it. So suppose let me just write it here. Okay, just write it here. Suppose let's take sigma just to be the time reversal, and then chi1, that means chi1 tilde t equal to chi1 minus t, and the chi1 chi2 tilde t equal to chi2 minus t minus I beta. So this minus t is crucial. And now if you do this twice, you get back to itself. So you have to use the property that the theta is a time reversal. It's a Z2 time reversal operation. Okay, so now let's look at a quick example. Let's look at a quick example. Will be illuminating to see this. So now let's consider example which we can actually calculate explicitly. Okay? Yes? It's actually minus I beta. It just depends on how you take this theta operation inside here. In the end, you do it carefully. It's minus I beta. This is minus I beta from my memory, and also it's minus I beta, I think, on my not very carefully written notes. So now let's consider a simple example of Brownian motion. Okay. Let's consider a very simple example of Brownian motion. So Brownian motion can be simulated by considering the following systems. Okay, so let's consider one particle. So let's consider the following Lagrangian, fundamental Lagrangian. Have one particle, just a free particle. Then I have a bunch of harmonic oscillator, say some n number of harmonic oscillator with some frequency spectrum. And then there's a linear coupling between this particle and those harmonic oscillators. Okay. And we will put the system at the finite temperature. Okay, so let's take the 0 just equal to 1 over z0. For simplicity, let's just take the thermal ensemble. Okay, just do the thermal ensemble. And now you can integrate out those Q's. Okay, these are just harmonic oscillators. You can just explicitly integrate them out. So you put this. So this is for single copy. You double it, put on this closed time contour. And then you can integrate out the harmonic oscillators. Okay? And when you integrate a harmonic oscillator because of this coupling, and then that will generate an effective action for X. Okay, that will generate effective action. So this is a calculation you can do explicitly. And so we can also just deduce what should be the action. Okay? We can also deduce from the action just from the effective field theory perspective. So suppose now you integrate out all those harmonic oscillator, and then we will get the effective Lagrangian for the XR and the XA, because the only thing left is XR and the XA. Okay, it's XR and the XA, and then let's just try to write down a low-range effective theory for that. Okay, so the lowest term you would write down first. Remember, because of this property, any term must involving at least one A field. Okay, so the simplest term you can write down, say for example, the lowest term would be say A, the XR and XA term. Okay, so this one does not have any derivative, but this term is not allowed because this original Lagrangian because this original Lagrangian. Because this original Lagrangian, essentially this is a free particle, and having such a term corresponding to you actually generate the potential for this particle. Okay, And so let me just say this term is not allowed. And then let's just look at the terms with the derivatives. Let me see. So the next order term would be xa partial t xr. And then you can also have two derivative terms, m, say, for example, m xr dot xa dot. Okay, so let me just put a dot. And then you can also, and these are all the term linear in xa. Now let's include a term which is quadratic in ma. Say now have to be pure imaginary, because now even terms in xa have to be imaginary. So let me just write it as xa squared. Okay, xa squared, etc. Okay. So this is the, of course, you can have cubic terms, have higher derivative, but the lowest few terms you can write down just this one. Okay, the lowest term you can write down is this one. And now you can impose. Oh, yeah, maybe actually maybe I will just do it at the beginning of the next lecture. Anyway, so now you can just look at this, and then this is your low energy effective action, and then we will see that if you look at this effective action, it just precisely recover the Brownian motion. Okay. Brownian motion, and that way we can also see how those constraints, what all those constraints corresponding to, okay, all those constraints corresponding to, and for example, this one, this one will just imply this sigma to be positive, and etc. Anyway, so let's maybe do it, better do it at the beginning of next lecture. Okay, so we will stop here. Why this is a causality condition? Yeah. So the causality condition here in the Brownian motion is related. So this term later will be identified as a friction, and you will see that this condition in the end will lead to that mu should be a positive number. So corresponding to the friction is positive, and friction coefficient is positive. If your friction coefficient is negative, of course we know that we'll have a pole in the upper half plane, then will not be causal. Yeah, we will have anti-friction. Yeah. Yes.
Is it clear why the force or requires?
So, yeah, that's a very interesting question. They don't force it. Somehow you have to combine them. Somehow you have to combine them. And so this is a little bit mystery to myself. Somehow only for time reversal system you can somehow so this is related to a lot of mystery which I actually don't fully understand myself. So as I mentioned before, that this condition will eventually lead to the second law of thermodynamics. This is your second law of thermodynamics. And once you impose this condition, okay, once you impose the time reversal and the local equilibrium, will lead to the second law of thermodynamics. And now if you look at all possible proofs of second law of thermodynamics, including the Boltzmann's H theorem, etc., always have to impose, you always have to assume time reversal. Somehow time reversal is crucial to have emergence of second law of thermodynamics. And so this is also reason somehow the time reversal seems to be crucial. Yeah. Oh, that's a good question. So the Kermes condition itself is normally formulated as a condition for equilibrium. In particular, people doing those algebraic quantum field theory, etc., they were hoping to prove. They have been hoping to prove that, say, if a system satisfies Kermes condition, then that system must be described by a thermal density matrix. So in that sense, that you can equate these two. you can equate these two. I think people could not really prove it for infinite dimensional systems, but they can prove it for finite dimensional systems. Yeah. Yeah.
So what the time
Yeah, that's a good point. Yeah, that's a good point. But it's but the leveless you can still think. Well, you can still think maybe you don't have. Yeah, I think you can still. Yeah, it just say the second node no longer in the. I think the entropy is still. The second node still is a sensible. Is still a sensible thing. It just no longer have the unique status to give you an arrow of time. Just you already have, that means you already have some kind of arrow of time you can distinguish by some others. And you don't have to use thermodynamics to determine arrow of time. But the second node is still a non-trivial statement, even without time reversal. Yeah, just the thermodynamic arrow of time will not be the arrow of time. Yeah.
Unitarity conditions include causality. Is there a feature of zero-dimensional?
No, actually, it's a little bit more subtle.